So you mastered one-dimensional motion. You got that down. So now we're going to throw another dimension into it. We're going to make this two-dimensional. The dimensions we're going to deal with are on the x-axis and the y-axis. We are not going to the z-axis. It's just not a good idea at this level. So we won't be going there. Go on in physics and you'll get to go to the z-axis. Have fun all by yourself. I'm not going with you. The quantities that we're talking about, we got to distinguish between scalar and vector quantities. And we kind of started to do this in the last chapter. We referenced it, but we didn't really dive into the details. You can describe every single physical quantity you've ever talked about as scalar or vector. And if it's scalar, there's no direction to it. Temperature is scalar. 32 degrees north. Well, that's a whole different thing. But anyway, when we talk about a scalar quantity, we do not have to specify direction. It's just magnitude. It's all magnitude in units. If we're talking about a vector quantity, it's got both a direction and a magnitude. So we have to specify the direction or it's not meaningful. Okay, easy enough. The little note cards that you were following in your lab, vectors or scalar quantities? Vectors, right, because you had directions with them, which you followed admirably. Okay, so we can track vectors. And you did a little bit of this, and you're doing a little bit of this in the lab. When you track vectors, it's really handy to have a picture. Did anybody resort to drawing pictures to find their object? Anybody try that? Anybody think of that? I'm an insanely visual learner, so I tend to make maps of everything. That would have been one of my first go-tos because of how my brain works. You can't add vectors with different units. So your vector quantities that you were following should have all been in the same units, which were meters. Hopefully nobody put centimeters on their card. When you have vectors that you're looking at, you got to make sure that you're looking at similar quantities. You can't add temperature and time. You can't add distance and volume. You can't add displacement and velocity. So we're going to start to look at vectors on a graph. So if I tell you to go 2 meters north, 3 meters west, 1 meter south, 1, 2, 3, 4, 5 meters west, 3 meters north, and 1, 2, 3, 4, 5, 6, 7, 8. 8 meters. What's my displacement? One, 2, 3, 4 meters north. I went an awfully long way. I wasted lots of energy. Lots of time, lots of going in circles. Anybody feel like that after they found their object? I don't think anybody in here did the evil thing that I've almost always had one group do, which is that the starting object and the ending object are the same. Oh, did you? Okay. They just took you on a big giant loop. Okay, I figured I would have one group do that. Usually do. So remember, displacement and distance are not the same. If we want to keep track of these vectors, using a picture helps. Now, you notice, and I will expand this so we'll blow the scale all out of whack. What did I put on the end of each of these vectors? Arrowhead. That's really critical. I can't overemphasize the importance of that stupid little arrowhead. It matters. When you've got multiple vectors, you're going to see why it matters. When you are breaking apart vectors, you're going to see why it matters. Because when you're finding resultants, you're going to see why it matters. Okay. So we said that back when I had a scale, we could give all the directions, all the little individual vectors. I went 2 meters north, 3 meters east, 1 meter south, 5 meters east, 4 meters, whatever. But my displacement is just that 4 meters. Well, that displacement, that final actual displacement is we'll just go back to here. I had all those individual vectors, but when I added them all up, what I got was called the resultant vector. That's that overall displacement. And if I look at this, so if this was, what, 2 north, oh, put in your units, Moser, 2 meters north, and I went there, what, 1 meter south, and then I went 5 meters north. Can I add those up? I can. And I get, do I get 8? What do I get? Well, here's the thing. Here's the funny thing. Let me shrink that back down. If I go 2 meters north and 1 meter south, what's my overall displacement north to south? 1 meter. Because in essence, that southward motion acts as a negative. Remember how with one-dimensional motion we talked about sign as a proxy for direction. When you're adding vectors, it's the same thing. Did any groups here eventually, finally, in frustration, take all their cards and go, okay, look, we went a meter north, we went a meter south, throw that out. Okay, we went 10 meters east, we went 10 meters west, throw those out. Anybody do that at the end? Is that what finally got you there? Okay. Because, so if we have 1 meter north, or 2 meters north, 1 meter south, 1, 2, 3, 4, 5, what's our overall displacement? Yeah, 1, 2, 3, 4, 5, 6 meters. When we're adding vectors, what we get is a resultant. And it's just the displacement in the end, as long as we're talking about distances. We can talk about other things, and we will. But we can add vectors and get a resultant. When we want to start talking about vectors, the easiest way to do it is by drawing them. And we're going to first learn how to resolve vectors visually. So these are graphic representations of motion. This is the point in the year when we will use protractors, yay, and graph paper, yay. And we're going to talk a little bit about orientations. I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 meters east. And I'm going to put a little compass rose on there. You're all familiar with the compass rose, north, south, east, and west. It's a handy thing. And I'm going to say that I have a motion, a direction of travel that is 12 meters to the east. And then, remember I have that arrowhead on there, so I'm showing where the motion started and where the motion ended. You probably want to draw this. Then I'm going to go 1, 2, 3, 4, 5 meters south. Okay. So I have 2 bits of travel. I have my first vector starting there, ending there. My second vector starting there, ending there. Note that each of those vectors is head to tail. So I always have one arrow head butting up against sort of the flat end of the vector. To draw in the resultant, I'm going to draw in my overall displacement. Where does my overall displacement start? Well, it starts here at point A. Let's call that A, B, and C, I guess. And it goes, and this is where using the straight line feature on Doceri is a brilliant idea. It goes like that. And note that I put an arrowhead on my resultant vector too. Why did I put an arrowhead on my resultant vector? Because it tells me where I went. That arrowhead is really pretty important. That arrowhead matters. Now, we can figure this out algebraically. You all know how to do Pythagorean theorem. It's easy. But what we're going to start out doing is actually drawing this to scale and measuring it. We're going to use actual rulers and meter sticks, and we're going to use an actual protractor to find this angle. Later we will do that with trig. We'll do that with algebra and trig, but right now we're going to start off doing it graphically. But before we do that, I want to have a word about directions. So I said that we were traveling east and south. This line right here, if we imagine that we have superimposed, I'm going to put this in one more color. Sorry if I have anybody in here who's colorblind. I have a limited palette from which to choose. I'm going to use green here. If we superimpose that compass rose on here, that vector we find is to the south from the east. We call that south of east. We know that direction of travel is south of east. We are describing this angle here. That's going to become important. So let's practice one. And I haven't, hold on. Insert images after the fact. That's on the recording for anybody who needs it. I'm just going to use the numbers from this. We've gone 12 meters east and 5 meters south. We want to know what the overall displacement is. If I'm going to do this graphically, I am literally going to use a ruler or a meter stick, and I'm going to use a protractor, and that's how I'm going to measure that displacement. So the first thing we want to do is use a reasonable scale. If you're sitting there using a regular sheet of paper and you've got a regular ruler, 12 centimeters is not unreasonable. You can fit that on a paper. You can do a meter equals a centimeter. You can get crazy and say that a millimeter equals a centimeter. What I'm going to tell you is, at that tiniest scale, it's really, really hard to read with the level of precision that you want. So I'm going to do up here, I'll do a decimeter equals a meter. So I'm going to do 120 centimeters and 50 centimeters because that'll work for scale on the board. Okay, so I've drawn my vectors to scale, and now what I need to do is I need to impose the resultant on them. And I'm going to draw a line connecting the tail of the first vector to the head of the second vector. And my resultants on the actual board. And note that I labeled it R for resultant. What could we label, what could we label these things? That is what? Delta X. This is delta Y. This is neither delta X nor delta Y. That resultant has got a delta, it's got an X and a Y component. It is made up of two other vectors. So we can't describe it on just the X or Y axis. What you're going to do is take your ruler and actually physically measure that line. And you're all going to get different numbers, so write it down. Write down your value for R. I'm going to try it up here, and it's going to be terrible. Okay, when I measure the line on my board, I am getting 131 centimeters, which would be a resultant of 13.1 meters. What are you getting? Okay, we use these as a tool for estimating how close we are to a value. We found the magnitude, and so now we're going to find the angle. And what we're looking at, if this is our starting point, is that angle. So again, we superimpose our compass rose, north, south, east, and west, because we're dealing in north, south, east, and west. We're going to deal with some that are not dealing in north, south, east, and west. So we're going to superimpose our compass rose, and we're literally going to take a protractor and line it up to that. So when I line up my compass that way, I get about 40 degrees. And the question is, 40 degrees what? This is where we have to think back to the compass rose. That is 40 degrees east, or I'm sorry, south of east. So I would give my resultant here, if I was asked for a final answer, as 13.1 meters at a heading of 40.0 meters south of east. Okay, what did you guys get for angle?
23.5.
What'd you get? 23.5. 23.5? Hold on. that as a teachable moment. I said, oh, my line's a little fudgy at the end. How bad could it be? If I redraw my line more carefully, I get something that's agreeing more with your between 20 and 25 degrees. And that 40 starts to look pretty outrageous. I'm going to delete it, actually. How embarrassing. Oh, and I put in meters. Good God, what am I thinking? I'll say 23.0 degrees south of east. Okay. So yeah, just a little fudginess in the line can really throw off your measurements. The longer your lines are, the more that fudginess will tend to affect your final numbers. So let's real quickly talk about one other kind of example with these. And I know, it's a little rough, but I'm better at drawing bunnies. So we got an airplane. We get a lot of these, airplane, helicopter, etc. problems. If this airplane goes along a runway for some distance, so let's say it goes along a runway for 100 meters, some sort of advanced military secret aircraft that can do a 100-meter takeoff. Fantastic. Only in a physics problem. And then it takes off at an angle of, let's see, 37 degrees above the horizon. You'll sometimes see that given as above the horizontal. If I want to find its resultant displacement from point A to point B, and it travels at 37 above the horizon for 20 meters, and then it probably has to change its approach angle because that's pretty crazy steep. Can I find the resultant of that motion graphically? Sure. There's the resultant of that motion. Now, this is clearly a delta x. Is this leg a delta x or a delta y? No, it is itself sort of a derived vector. It's the product of an x and a y. That's okay though, because right now with graphics we're not too worried about that. You can draw this to scale. You can measure it. I'm not going to walk you through practicing the measurements on this one again, but here's the thing I want to caution you about, and here's the thing that I have seen again and again and again people screw up on tests, so this is why I'm addressing it head on early. When you find this angle, and I'm giving my wildest guess here, I'm going to say it's like 12 degrees. 12 degrees what? North of east? 12 degrees above the horizon. There's no north, south, east, and west. We don't know what direction this runway is pointing. We have no idea. And furthermore, we're looking at this at a side view. So we're talking about travel along the horizon and then travel above the horizon. So I just want you to be really cautious about that. The other thing is, let's just briefly look back at this compass rose. North, south, west, and east. Whenever you're thinking about angles, there are two ways to describe every angle. We can describe this angle as being east of north. We can describe, this heading. If we describe this heading using this angle, it's east of north. We can use the same exact heading, but describe it with a different angle that is north of east. Okay? So that's fairly self-explanatory. I'm going to give you some practice problems doing graphicals, so you will need the ruler and the protractors, and then that's probably where we'll leave off for today. That is where we'll leave off.